Hello everyone, I am Shrimanti Ghosh. I am a postdoctoral fellow at the Department of Radiology, University of Alberta. Today I am going to talk about my research project on AI-driven automated detection of shoulder rotator cuff tears using ultrasound imaging. Our main objective is to develop an AI-based tool to automatically segment the relevant structures in the shoulder and detect full thickness rotator cuff tears automatically from ultrasound images. AI detection of rotator cuff tear or RCT from ultrasound can be very much beneficial for non-specialized providers who can quickly detect RCT. It can save costs and reduce long wait times for patients. It can be beneficial in remote areas as well where specialized expertise is scarce. So just to give you a little background on this, chronic shoulder problems are the second most common orthopedic concern after knee problems. And so that is why precise classification of rotator cuff tears benefits from segmentation of relevant structures for more precise diagnosis and treatment planning. But expert manual segmentation is tedious, time consuming, and expensive. On the other hand, ultrasound is a faster, cost effective alternative to MRI to detect RCT. But ultrasound images are very challenging to deal with due to its speckle noise, low contrast, and various artifacts. That is why we think AI can help us in this case, and that is why our plan is to develop an innovative AI driven, fast, cost effective ultrasound tool for RCT detection. These two images you can see, one is the example of an intact tendon, and the other one is the torn tendon. For the study, we have used the dataset of 210 patients with MRI confirmed ultrasound image sets where intact tendons were from 100 patients and torn tendon were from 110 patients. There were total 14,500 2D ultrasound images in total. It is divided into 80% for training and 20% for testing. Five-fold cross-validation was performed during the training of all the deep learning models that we have used. Manual segmentation or the ground truth was performed by expert radiologists and medical students. These are the examples of the original ultrasound image and the corresponding manual segmentation. Now, the methodology. The methodology or our main framework contains two major steps. The first one is the segmentation model, and the second one is the classification model. So, in the segmentation model, the input to the model is the original ultrasound image, and the output of the model is the segmentation contour points. So, segmentation contour points are nothing but the collection of XY coordinates, and if we combine the XY coordinates together, we can get a vector of a dimension like this. Let's say 400 by 1. For the segmentation model, we used a fine-tuned CNN, that is the Inception V4, and along with that, we used an autoencoder as well. The reason we used autoencoder here is to reduce the dimensionality of the vector. So here, autoencoder reduces the dimensionality of the vector, and the decoder part of the autoencoder reconstructs the original segmentation contour point. This is a landmark based segmentation model. This is not conventional semantic segmentation model. This is the first step. After that, we used a classification model, that is the VGG16, and the input to this model are the original ultrasound image and the segmentation mask that we got from the previous step. These two are the inputs to the classification model. After that, the classification model predicts whether it is an intact tendon or it is a torn tendon. These are the implementation details, such as the learning rate, batch size, and the number of epochs. The training time was 8 hours and the prediction time was 5 milliseconds per image on Compute Canada. Now the results of automated segmentation method. Here we use dice coefficient and Hausdorff distance as the evaluation matrices. Our proposed method, that is the CNN plus autoencoder, it achieved 95% accuracy in segmenting the relevant structure in terms of dice coefficient and 2.9 millimeter Hausdorff distance. So higher the dice score and lower the Hausdorff distance corresponds to better segmentation. You can see the other unit-based models could only achieve 92% accuracy maximum, whereas our method achieved 95% accuracy. After that, the classification results. Our method achieved 85% accuracy in classifying the shoulder rotator cuff tears as, intact or torn, whereas the other CNN-based classification model could only achieve 81% accuracy. So these are the visual results. You can see it's the segmenting humeral head. The red one is the ground truth. The green one is our proposed method. And the yellow is the unit's performance. You can see unit is actually not able to capture the small little details like here and here. Whereas our method could actually capture the small little details. Similarly, for the bursa, another structure, you can see here, the last one, the unit is not able to capture this part, whereas our method could capture those details. Our proposed approach, deep learning based approach, it achieved 85% accuracy in the classification of tendons as intact or torn. Focusing on highly visible tendon tear regions enhance the explainability in the diagnostic process. This can be used by lightly trained healthcare providers at point of care facilities. This can reduce costs and wait times in the emergency rooms as well. Ultimately, our aim is to build trust in AI for clinicians and patients. So, as a concluding statement, we can say that we are developing a valuable ultrasound based AI tool to improve diagnosis and treatment planning, reduce wait time, and save costs. We are really grateful to all our funding sources and thank you so much.